Okay, so, and just to point out why the connections are here, I want to go back to this. This is actually related to the paper that I handed out previously. The paper has a correlation of entropy with enthalpy for a reaction that is the heat of, a reaction that is the heating of that substance from 0 Kelvin to room temperature, standard temperature conditions. What they did is they basically took the energy needed, the H, this is the H axis, needed to raise a substance from nearly 0 to temperature of room temperature at standard pressure. And you can measure that. You can basically heat up a substance, and you can measure how much heat it takes to deliver the system, to heat the system up. And you see it's related to the heat capacity and the change in temperature. But what's the thing is, we can also get, so this is something you can measure in the lab. Remember that this is chapter 1 concept, the delta H's. The S is a different chapter, actually. When we're talking about entropies, we talked about how you could get them by heating up a substance, but you can get them in tons of other ways as well. And you always get the same number, and so you express that as the entropy. And so people have gotten those experimentally and expressed them. So we're comparing the standard entropy that you get from the table, could be gotten in any way, to the delta H of the specific reaction of heating the substance from very, very cold up to room temperature. There's no reason for those experiments. Those experiments are not necessarily the same at all. And the experimenters are very different. They combed the literature and they got all this data out for these people that calculated these two things. And it turns out that if you plot all those together, those are not independent variables. Those are definitely related, just like with our PCA analysis, actually. In fact, you can even say, they even talked about the data like data point 72 that's a little bit off. They talked about why that might be a little bit off. They actually went into it. It's even more accurate than it seems. There's a flat line. If you take y over x, s over delta h, you get a constant that is 0.0066 per Kelvin. Okay? That is actually, there's actually a reason for that. They go into that in the paper. If you take the thermodynamics of it and you divide those two, you get exactly that number. So if you take the equations and you divide it, you see that you should get that number. And that means that entropy is closely related to the enthalpy of heating. And in general, this also relates to heat capacity. Diamond, so what's the different substances? So number 1, way down here, is diamond. It turns out that diamond has an incredibly low heat capacity. Graphite has a higher heat capacity, same atoms, different arrangement. But it turns out that diamond, because it's so stiff and small, that it actually has widely spaced heating levels, widely spaced energy levels. And that makes it, when you heat it up, it heats up very quickly. Or actually, the delta H is very small, and that goes with the small s. Copper is medium. It's number 14 on this graph. Because there's these really big numbers, you can say lead is 38, and you actually get the even bigger things. But they have things like sucrose and all sorts of things. So basically everything that they can think of, they pulled it out, and they found out that without any collusion among the researchers, they didn't know that their data would be used this way. But it shows that there's a beautiful relationship between entropy and enthalpy. So entropy, and I should be very clear, enthalpy, you should always ask of what reaction. Entropy and enthalpy of heating are very closely related. Okay? You can look up and down. You can see if what kinds of different substances they had. They had like dichlorobenzene, and they even have sucrose, I think, somewhere here. You know, they don't get too big. Yeah, there's sucrose there. Very different atoms. They all follow this line. So entropy and enthalpy are related. Different forms of entropy are related. And this answers our question. Everything cools as it expands, because anything, even marbles in a box, even an ideal gas, the entropy of the system, if it can be expressed as configurational and thermal entropy, that equals RT times the natural log of the number of microstates that we had. And as your volume increases, your number of configurational microstates increases. This value increases, configurational entropy. Remember that S is very closely related to Q over T. It's defined as that. And so what you have is if the system is closed and isolated, no heat can be transferred out of the system, so this heat must be zero. Q must be zero because it can't, the heat has to be going somewhere. The microstates have increased, but there's no place for the heat to move to. You can't have a delta S. When a gas expands, the configurational entropy increases, this term. If it's isolated, then the thermal entropy must decrease. If it's isolated and not kept at constant temperature, you have to keep S system constant because you haven't changed anything else. If this number goes up, this number must go down. That means you have fewer thermal microstates that the system is accessing. That means it gets colder. It stops moving in one place as much. You're letting it expand in a big dimension. On the smallest dimension, it's not moving as much because it's moving more in the biggest dimension. You can apply these physics concepts here. So the universe, this is a slight case of understatement. The universe is very isolated. It has no surroundings to exchange heat with. So like an ideal gas, we would say we know that the configurational entropy has gone up since the Big Bang, and therefore the thermal entropy of the atoms moving randomly should go down, and everything should cool down. Except for one little thing. There's one little detail that I haven't mentioned, one fly in the ointment. If S conf goes up, then S therm must go down unless, well, the second law says not that the entropy of the universe is equal, but that it's increasing. We have to account for that as well. That's the last slide. Okay? What about the second law? Well, okay, so delta S of the universe, by the second law's definition, is greater than zero. And so you could say, well, it doesn't have to cool down, but the thing about delta S of the universe is just saying that it must increase. It doesn't say it must increase maximally. So it turns out that if configurational entropy increases fast enough, that takes care of, that already increases the entropy of the universe. And in a sense, it can pay for the entropy of other parts of the universe to go down. It's actually like the system and surroundings again, except it's different kinds of entropy. So if your system is the universe, then you have this equation. If this equation is actually a greater than sign rather than an equal sign, then all you have to say is if I just have a big enough delta S configuration, then I'll still get the delta S therm less than zero. Things will still cool down. If I have a big enough configurational space that it's accessing. Well, what's one of the things that we know about the universe? Delta S configurational is really huge. So we're in a universe that pretty much has to cool down because it's expanding so much. A huge universe actually makes sense if you look at it in a PChem kind of way. You need a huge universe to have it cool down. Because anything cools when it expands, entropy caused the formation of stars and the Earth. And because the configurational entropy was huge, the cooling down was also huge. Okay? And this is, I'm going to have a few quotes from R.J.P. Williams. The cooling of the universe due to expansion was one major cause of the natural selection of the chemical elements. One of the reasons why we use the elements we do is because of the way the universe cooled. Because we're at this temperature, temperature affects chemistry. Now we are not at 0.3 Kelvin like the rest of the universe, like most of outer space. We are at 300 Kelvin. And that's because we had sources that were keeping us hot. So elements in the Earth's core decaying, that gives off heat and that keeps us hot. And as long as we stay around 300 Kelvin, water could form on the surface, and we need water for life. And R.J.P. Williams puts it this way: the natural selection of the chemical elements decided, I love it when he uses these anthropomorphic, it kind of blows my mind. The natural selection of the chemical elements decided that the only liquid on the Earth's surface 4 billion years ago was water. If the temperature had fallen lower, CO2 had been the only gas available, solid carbon dioxide would have formed. And you see that on other planets, but you would not have oceans of carbon dioxide. It turns out that it's actually kind of hard to get a planet with exposed oceans, and we haven't found another one yet. There's chemical reasons why that's difficult, and why water is the best explanation for why we can have liquids, and therefore why we can live and breathe and stuff. Okay. So that is what a data talk looks like. We go through a couple papers. I sort of connect them to different things. Chapter 2 homework is due on Friday, so I just want to remind you of that, and we will start Chapter 3.